Okay, so you are live, right? Okay. So, welcome everyone. So, I'm extremely pleased to welcome Professor Palash Dey from IT Kharagpur. So, he is an assistant professor in the Department of CSC at IT Kharagpur. So, before joining ITKGP, he spent around a year. So, he had distance his TIFR. So, before that, he finished his PhD and Master of Engineering from CSC department from ISC. And he received the Inspired Faculty Award in 2018 and ACM India Based Dissertation Award in 2017. So he has been a fellow of the West Bengal Academy of Science and Technology in West Bengal, India since 2022. And he's also an INE Young Escape since 2023. He is an ACM India eminent speaker for 2024 to 2026. His research focuses on algorithmic game theory and parametric algorithms. So without further ado, over to you, Palash.
So thanks, Abhishek, for this generous introduction, and special thanks for the invitation to you and SPCS and TI for more generally. So today I talk about problem algorithms which I was doing with my colleagues Shudeshna and two of my PhD students, Shlesha Hota and Shipra Singh. So it's a generalization of classic knapsack problems on graphs. Let's talk what is the classic knapsack problem. We are given n items which are sizes S1 to Sn, and each item has a profit or price whatever P1 to Pn, and I have a bag of certain size B, and I need to compute a subset of items whose total size is less than equal to that, which fits in the bag, and I have to maximize my total profit. That's the classic knapsack. It is NP complete, but it's not strongly NP complete. We have 8 peters for this problem. What do you mean by knapsack on graph? So some things we have observed that there are some network structure on the items of the knapsack problem. So, for example, look at this example. Suppose these are possible locations for cell towers, and these are their ranges. So, if I draw the graphs, each cell tower is a node, and I have an edge between two cell towers if there is an overlap between them. And as a company, suppose I want to open some cell towers, but I want my customers to get connected. So the question is, I have a given budget B. Each cell tower carries a cost and a particular profit. Profit in terms of the amount of customer revenue I may get from that area. So each vertex has a profit and a cost, and I have a budget. So the question is, how many which subset of cell towers I should open so that it's budget feasible, maximize my profit. And on top of it, the induced graph on the subset of vertices is connected. So that's the extra constraint. So these I called connected knapsack.
So possible locations are already known.
Yes. Possible locations are already known.
So why did you comment the entire graph?
I may not have the budget.
Okay.
Yeah.
I see.
So why it's a generalization of knapsack? If this graph is a complete graph, then it's a classical knapsack. Yes.
What does connectedness mean?
Suppose you choose, a knapsack solution is a subset of items.
Yes.
So you look at the induced graph on that subset of vertices, which are items here.
Yeah.
And that should be a connected subgraph of the given.
No. I follow the
definition. Okay. Yeah.
Why does connectedness make sense in this definition in this problem?
So for handoff essentially. For handoff, if you're moving from one point to the other, you would like the connection to be without interruptions. If you're connected, you won't wait the second.
No, that determines the way you are going.
However you go.
But that's exactly the cheapest connected subgraph.
The cheapest connected sub. Okay.
Second one is think of we have say 10 days and we are planning vacation. But I'm suppose I'm visiting TIFR and next I'll visit ISC Bangalore. I have 1 week in my hand. So which cities I can go and visit within my limited time. I have limited budget and so on. So here also again, if you see, I have underlying graph, and visiting each city incurs certain cost, and I have two special vertices, and my solutions, knapsack solutions, are paths between these two vertices. I want to go from city X to city Y, and each visiting each city incurs me certain cost and gives me certain incentive. So here the solutions should be maybe set of all paths from Mumbai to Goa.
But here, it
Yeah.
can easily be the case that the non-unique optimal answers.
Yeah. No. Yeah.
So
This
in
is
knapsack, you don't get that.
correct. So no paths. You may have many paths depending on. For example, you go from Mumbai, you can go to Kashmir and then come. So, but yeah, shortest paths may be less. But paths typically.
The optimal answer might not be unique.
No,
no.
have a benefit of visiting its city, there will be.
No. The optimal answer is.
Read the value will be.
I don't see anything.
Yeah, you have a budget, backside, and you maximize your reward. Now here comes the problem with if this thing is funded by government funds, then account development will ask, is it the shortest path? Have you taken the shortest path? So here this part, no, I need to take a shortest path from these two things. But again, combinatorially, again,
So here so it's the cost. The costs are on ages, right?
uh,
And there the value was on vertices.
So no, when I say shortest paths, these edges are weights and costs with respect to the shortest path with respect to 8 weights, and my knapsack solution is with respect to these vertices. Each vertex has a value and price. It's like the hotel price at that place, and that's the cost of staying at Mumbai maybe, and then whatever incentive I get.
Right.
So
So
that
there
is-
is no age cost, right?
Age cost is the transition cost of time, and when I say shortest path, I mean the age cost. I will only take care of age cost.
You only
The
see the
shortest-
vertices, then you get the induce the graph for free.
Correct. Yeah.
Okay. I see. But the best solutions in the original graph are right.
Yeah. For example, if I use the age cost to be the length of the path, then this is exactly the account development will ask me, have you taken shortest path?
Okay.
Yeah. Here are some more things. So as he asked, why not cover all regions? So suppose these are the regions where people stay. So which locations you will install towers, and so your solution here should form a vertex cover. Okay, and you can generalize these to others problems on set family, for example, set cover or hitting set. In set cover, we are picking sets. In classical set cover, those sets has only costs. Now they have some profits also, and I want to compute a set cover subject to knapsack, that I don't exceed my knapsack budget and maximize my knapsack profit. So all these problems are, in some sense restricting the feasible solutions of knapsack. In classical knapsack, all subsets are feasible solution, but here these are not. Only some subsets are feasible solutions. Question? So in the rest of the talk, I just picked few of the results. I just explain few of the results which basically convey the main ideas. So here is let's begin with some very easy results. We show that connected knapsack is strongly NP-complete, and it's a very easy reduction from vertex cover. What we do, we subdivide each edge like this, and we have a global vertex which we connect to every original vertex, so that and this global vertex has size 0 and price 0. So you can take the global vertex as free, and that ensures connectivity. You don't have to take care of connectivity. Think about connectivity. This new edge vertices has size 0, so you can always take them, and they give profit. But these original vertices have size 1 but no profit. So if you are looking for a vertex cover of size k, then you define back size to be k, and your target price as a decision version of this problem, target price is m. You want to pick all the edges, and by picking k vertices, k original vertices, you want to be a connected thing. The connectivity will get ensured by this global vertex, but you have to, because the end solution should be connected, you must pick at least one endpoint of every edge, which is a vertex cover. So it's fairly easy to see that this original graph has a vertex cover of size k, if and only if it has a, this is a case instance. There is a vertex cover of size k, which achieves a price of k. So you say pick this vertex cover and pick the global vertices and pick all the edge vertices.
What is strongly implemented?
Strongly integrated means that if you have numbers, this is empty complete even when the numbers are polynomially bounded. So we have the numbers all are small numbers. So we do not expect a 8 test for this problem. So we should hardness for trees also, in particular for star graphs also. But here we won't have strongly empty completeness. Because
Are they the same thing, not having an empty task and number be bounded?
One direction I am sure that if you have strong NP completeness, you do not have FP. I am not very sure about the other direction. Are they equivalent or not?
Is it easy to see why?
Sorry?
Is it easy to see why?
Yeah. It's just you set epsilon to be small enough and exploit the fact that the solution is integral, something like that. So, for example, if you have numbers and the numbers are integer, which you can assume without loss of generality because computer is finite, they are rational numbers. So they are integers, and then you set epsilon to be 1 over poly n, which will force any x1 plus epsilon approximation algorithm to output an optimal solution in poly n time.
So what is an example from that is not strongly implemented, like subsets?
No. So for example, takes the weighted vertex cover. Weighted vertex cover is strongly integrated to what is the example of? Not strongly integrated. Knapsack.
And that is because
Because you have an FP. You
basically the parameters are bounded. Oh, okay. Oh, I see. So if the parameter is bounded.
Yeah, if the parameter is bounded, you have a dynamic programming algorithm, n times.
So there is no way for now.
Only if FP task has a complexity that depends polynomial in one number.
Yes. FP is running time is poly 1 over epsilon and n input size. Yeah.
Okay.
Oh, here is another easy reduction. We reduce from knapsack problem to this connected knapsack on star. Simply add a global vertex whose value is 0, weight 0, and connect it to everyone. So you always pick this global vertex and get connectedness as free. And hence, if there is a subset of items whose size is at most b and size is at least b, then that same subset gives you the solution here. And what we show here or this
Just for this figure, I'm also getting confused. So the reason is just that because if the small values will imply the solution itself is a small size, so you can do a binary search just by putting epsilon to be like 1 over poly.
Correct. Either binary search or if you have n numbers and the solutions are integral, if you expect to be epsilon to be small, then the
but the small is only 1 over poly. That's the
1 over poly n correct. 1 over poly n correct. Yeah. For example, take set cover. For example, take say unweighted vertex cover. Now, if it has a FP, then I will ask, okay, give me a 1 over 2n factor approximation algorithm.
Yeah.
Now it has to output an optimal solution.
I always thought that epsilon is a constant, you define however you want. So
No, epsilon is a parameter you can set. It's a part of input.
No, that is not that. So that is not that. Include theta, so theta and beta. It's polynomial in all the inputs, including the approximation.
Yeah. So beta is, n to the power f of 1 over epsilon.
Then it will be like log of it.
So-
That is like
No, then it becomes one. Yeah. Then there's no point of an approximation.
So in Peters also you can fit whatever epsilon you like, but the runtime is n to the power 1 of n to the power big of n to the power f of epsilon. Now your runtime cannot be polynomial. And there is another thing is called e-Peters. E-Peters is runtime is f of epsilon times polynomial. Times polynomial. This word product here.
What does E stand for?
Efficient. Yeah, efficient Peters. Yeah. And it has a nice connection with parametric complexity. If you have if some problem is W hard in parametric literature, then it cannot have an Peters. And again the same thing, because then you can use that.
have you defined a G Peters?
No, I didn't.
Going the other way, F E X.
Okay, yeah.
D
Okay, so then next what we will show is that for trees we cannot hope to prove strongly NP completeness because we have a pseudo polynomial matrix. For any tree, if the underlying graph is a tree. So connected knapsack, I want my solution. The induced graph on my solution should be a tree, and the underlying graph is a tree. Under this assumption, we have a pseudo polynomial algorithm. Again, what is a pseudo polynomial algorithm? Its runtime is poly in n and sum of the values of the numbers. And it's a dynamic programming based algorithm where we are storing some partial solution at every node. So suppose U is a node, and what we are storing is set of for every partial solution. We store and solution is a subset of vertices, so subset of items. We store this pair, their size and price. This tuple we store, and for which solutions? So remember, U is a tree. Remember the underlying graph is a tree. We first make it rooted arbitrarily at any node. So I now have a rooted tree. Now let me discuss what I am storing at a node U. So at U, I look at the subtree rooted at U, and all the solutions of the subtrees rooted at U. For all solutions, I am storing the size comma price pair. Now but the number of solutions could be huge, right? So there is the catch. I am storing only undominated solutions. What do you mean by undominated solutions? Very natural. So if I have a solution whose size is 3 and giving me a price of 5, I do not need to store a solution whose size is 3 and give me a price of 3. So this then I would say that this solution 3, 5 dominates 3, 3. Same here. So 3, 5 dominates 4, 5 because the price is same, but this set has weight more.
But this is just like for efficiency, right? I mean, you could have stored all of them.
But then yeah, just for
Columns.
no, not
You can store one candidate of each type.
correct. Yeah.
Sorry, why is showing all not positive?
Sorry? Because there would be like infinite, like there will be lots of like possible different solutions of the same value.
For that, yeah, we have to store the value, not the solution.
But that will have some problems that will not work here. In this, I'll discuss in the next slide.
Oh, because you cannot maintain this.
No, I'll have some problem. I'll just come. So I think the dominating makes sense that if you have a set with size 3 and price 5, it does not dominate this set because its size is small, but price is also small. That's fine. But it dominates this also. Right? Price is small, but size is small. So I only store undominated pairs in the sub undominated solutions, undominated pairs for the solution in the subtree iterator. And for U, I store two kinds of solutions. In DU, I store all the solutions which contain U, and in DU bar, I store all the solutions which contain U bar. This basically I need to update to maintain this DU.
Yeah, DU doesn't contain.
Oh, it doesn't contain. Yeah. So yeah. So let me put this example. So here is one tree. This suppose this is U. So what is DU? This is all subsets, all connected subsets of this subtree which should pick U. Now, for example, 1, 1 this is there. Then this is another one. I think this is 4, 5. This is another one. 5, 8, and this entire this 3 is another one. 8. That is DU, and DU bar is again all solutions, but it should not pick U. So
It's not correct.
no. For example, it can this only singleton set. Singleton, no.
Oh, not span.
Yeah, it's not pan. This solution. So obviously, I will always have 0, 0. I may not pick anything. Then 3, 4, and this 4, 7. This is the DU bar. Okay, so I just maintain these sets, and at the root, I will have the solution. I'll go over DU and DU bar, and whichever is has highest price, that's the solution. Because whichever pair has size more than back size, I don't store, because they are not going to lead me to a solution. So at the root node, I just go over these two lists, and whichever has the highest price, that's the output. Okay. Let's see how we can bound these things. First, you observe that no two pairs can have the same size. Because if the size is same, then profit also cannot be same because they are distinct. But then if the size is same, one must dominate other. So no two pair should not have the same size. So it can have at most the size of bag, B, many elements. Similarly, if P is the total price of all the items, then the cardinality of each of these set is at most. So the cardinality of each of these set is at most minimum of B and A.
So you are assuming everything is integer, right?
Yes, everything is integer. Everything is positive integer. Okay, so then how do I populate this? So we fill up this DP table bottom up. That means from root to from leaves to roots. For leaf nodes, suppose if U is a leaf node and I have to pick U, then that is the only solution. And if I can't pick U, that is the only solution. Empty set is the only solution. Otherwise, let's assume that U has these children V1, V2, Vk named arbitrarily. So we create this DP table entries iteratively. In DUI is basically DU as in the world where you had only children V1 to Vi, as if Vi plus 1 to Vk does not exist. So DU0, that means U does not have any child. That is this, as simple as this. And DUI. So I compute DU0, U0 from DU0 to DU1, DU2, and so on. And DUI is undom is, that means I remove all undominated pairs from this set. That is that undom operator. So what I do, I for every pair of U comma DU comma I minus 1 and every pair of DVI, that means every solution of subtree VI and every solution of this part, there is some type of that I add, because it is basically I combine these two solutions. On the other hand, U bar is very simple. If you don't pick U, as he pointed out, as Piyush pointed out, your solution must be entirely in one of these subtrees. So you take all pairs in all the subtrees and you remove combinated pairs. Okay.
VR should be D bar VA.
Yeah, there is some typo. Actually, these took more time than I estimated. I finished 5 minutes ago. Very sorry. There is some typo here. So the runtime is n if I have n nodes, and this undominated, removing undominated pairs, even if I do brute force, then in coordinate time I can do.
So this removing undominated pair is some sort of a cut and paste in.
Yes,
You have.
yes, cut and paste argument, correct. For proof of correctness, right? Yeah, cut and paste argument, yes.
So what does that mean? When you have a solution where for this sub, like its restriction to this subtree is dominated by somebody else, you chop this part off, stick in the that thing, and you only
You have a better
increase the
solution.
optimum and maintain the result.
Exactly. So now next what I do, I extend this algorithm to arbitrary graphs and with respect to treewidth. So treewidth is a notion, let me briefly introduce. For any graph, I can do what is called tree decomposition of a graph. Now, what is a tree decomposition of a graph? It is a tree wherein in every node I have some subset of vertices. So I have a tree. At every node corresponds to some subset of vertices with certain conditions. What are the conditions? Every vertex must belong to at least one subset. These subsets are called bags. Just to differentiate between from these subsets. These are vertices, these are bags. So first condition is every vertex of the graph must belong to at least one bag. Second condition is for every edge, say Gi, there must exist a bag which contains both the endpoints. Gi, for example, Jk, here is Jk. So every edge, so this is sometimes called every edge is realized, every vertex is realized, and for every vertex you look at the bags which contain that vertex that must contain a connected piece in your tree. So, for example,
It must be right. It's not,
sorry,
should not just connect. It should be just connected.
it should be connected. Yeah.
It's a connected it's a subtree.
Yeah. Connected piece of a tree is subtree. Correct. For example, if you look at E, this E. So this should be connected. Okay, so this is a tree decomposition of a graph. Not very natural definition, but it turns out that many algorithms. This is algorithmically very useful. There are various ways to define tree likeness of a graph. Natural one could be how many cycles it is. Tree has 0 cycles, maybe few cycles. Another natural definition could be what is the minimum number of vertices or edges you can delete. Size of feedback vertex set or feedback arcs. Etc.
For one thing.
Sorry.
You can move. So you told the bags, there are three conditions. One is each vertex should be in some
Bag.
No. Each edge should be in some bag.
Correct.
Then when do you draw edges in this between two bags?
I'm given a tree.
Tree that satisfies the conditions.
Any
Any tree. Yeah. It did not
It
mean
on the back. It could be an arbitrary
Tree
tree
on the back. Then every
Correct.
vertex is going to aggregate to it. These are
Correct. For example, you can put all vertices in one bag. That's also a tree decomposition. It's not unique. Tree decomposition of a graph is not unique, and the tree width of a tree decomposition is the size of the largest bag minus 1. Why minus 1? Just to ensure that the tree width of trees. That's it. So with this, it takes some time to get used to this concept. So you can show that the tree width of any tree is 1 and complete graph on n vertices, that its tree width is n minus 1. Okay, now let me give a high level idea of what basically I am doing. If you look at, for trees, what I'm storing here is how a solution can interact with you. It can either contain you or it cannot contain you. That's why du and du work. I am basically extending the same idea for bags. So at every bag, let XU with a set of vertices in the bag, and I look at all possible ways how any optimal solution can interact or intersect with that bag.
In the runtime, the n etc. is all in the denominator, like not in the bottom.
Yeah, it should be there. Yeah, it should be there. This is the result of doing assignment at the last one. Yesterday I was just roaming around. Yeah, it should be below.
Say it too loud. The students are also listening.
But now they know you're not. Yeah.
No, if the processor does it, why should I not? That's what they're taking.
Okay, so this runtime is like treewidth to the power treewidth, which is also known as 2 to the power treewidth log treewidth. So treewidth to the power treewidth, because you are for every possible partition of the bag, you are storing that repeatedly. That's why this treewidth to the power treewidth will be basically this, and then the rest is the same. There you are getting n and this minimum this square. I'm leaving it at this. Yeah.
Why not just you have to store each subset, right? So you have to do a table for every store like the same information you're storing, but now for each subset of each bag.
Correct. Not for each subset, for each partition of this bag.
Partition.
Because a solution is a subtree. Now,
A solution is some connected subgraph.
correct.
Oh, okay.
Yeah.
So, no, but the solution is just a subset of vertices, right?
Correct, but
all I can, the state is just whether a vertex is in the solution or not.
correct. That's true. But somehow you need to ensure that you need this information that which is already connected and which needs to be connected on top. So correct, which is the connected component. So I basically need to guess all the connected components of the bag. That's how this runtime is coming.
And in this case, your graph is
Arbitrary graph, but yeah, okay, yeah, there is something, but yeah, please ask the question first. Sorry, yeah.
Yeah.
Sorry, yeah.
The input is given as a tree decomposition.
Yes, that is very
Something compute, right?
Yeah, that's a very natural question. Yeah, computing a tree decomposition is NP complete, but there is an algorithm of this running time. True to the power tree, with which you can compute a tree decomposition. So
Up to some approximate.
if you want approximation, then you don't need treewidth to the power treewidth also. Then you can do in single exponential, I think 8 to the power treewidth. You can do approximate big of treewidth. So because of that result, we can assume without loss of generality that we are given a tree decomposition. And not only that, these trees could be arbitrarily bad. So there is some notion called nice tree decomposition. For example, nice tree decomposition has very nice properties. For example, the root is an empty. The bag at root node is empty. There cannot be so many kinds of nodes. All leaf nodes are empty nodes, empty bags. And there are few kinds of nodes, not all possibilities. Then people will go mad about enumerating over the all possible DPs.
So what is an empty bag?
This set could be empty also.
Why is there?
It's just there. It allows you, and this 3D composition allows you to keep this bag empty, and it just makes the DP easier. The initialization for empty sets is much easier. So each bag is a subset of vertices, possibly empty. Of course, if you have an empty bag, you can short circuit, not with it. But you can have the nice tree decomposition where, because these DPs start from leaf nodes, and if the leaf node is an empty bag, then the DP initialization is really super easy. Same with root node also. At the end, result is very easy.
And going back to the tree, so the runtime, so the treewidth to the treewidth comes because trying to get the treewidth itself.
And also the partition. For every partition.
Yeah, get a tree decomposition you're talking about.
And partition.
That also has treewidth to the treewidth, or those are just exponential in treewidth?
No. Partition. Number of partitions.
That's the use.
Okay.
Number of partitions of
dynamic programming is not just maintaining a table of all subsets at some particular all that. It's containing like the indices are by all partitions.
Correct, correct, exactly. So now again, we use this algorithm to get a fully FPT approximation scheme. What does that mean? There is a 1 minus epsilon factor approximation algorithm for this connected knapsack for optimizing price. So given a batch size, you want to maximize price, and this is the run. So how do we do that? The idea is we have a pseudo polymelting algorithm. That means which is polymelting algorithm if the numbers are small. So what you do is you scale down the numbers by scale down the numbers. So I divide it each price by epsilon p max by n, and then take the floor so that it's integer. That's important. And in the scale down instance, you run the polymelting algorithm. You see that for this instance, it is polymelting. The algorithm is polymelting. The runtime is to be for we go treewidth log treewidth times n times this. These are the prices. These are small poly n. It's a poly n. Okay, poly of n comma 1 by epsilon. So what is the algorithm? You scale down and find out the optimal solution W and output that, and hope that that's a good enough solution. So let's show why it is a good enough solution. Let O be an optimal solution. So this is L. This is the W is the set of items that the algorithm is output. This is their sum of prices. This is greater than or equal to this. Basically, if you take floor and multiply, you lose something. And then because for this instance, for the scale down instance, W is an optimal solution. If I replace W by O, this value can only drop. This summation can only drop. And then I get rid of this lower floor things by subtracting -1, and then I multiply this out, and this is opt, and this is P max. P max is less than or equal to opt. So this is greater than or equal to 1 minus epsilon times opt. So to begin, so P max is greater than less than or equal to opt. So to begin with, if some item has size more than bat, you can never take that item. You delete that item.
So what is fully FPT? I mean,
that is polynomial here. Poly of n epsilon 1 by epsilon. So So
It's FPT.
yes, FPT, because this is not.
okay, that's true.
This is the thing I came up with.
I think what he's pointing out that there are
Fully no, FPT is not F for not fully. Fixed this is not much aware. That's why this name I came up with. This is not polynomial.
So parameter is TW.
The parameter is TW, correct. So for when parameter is small, for some values of parameters, formally parameter is constant, then it is FPT. Yeah. Okay. So next, let's move on to next algorithm. Yeah. Just stop me when you want.
Yeah.
And because this is from my side, and okay. So here is another beautiful algorithm for path knapsack. So we have an algorithm of this sort of audible
Can you
runtime.
just revise what path knapsack means?
Yeah, path knapsack means I have given a graph. Again, each vertex has a weight and price, and I have two vertices, x and y. My solutions are paths between x and y, and then you solve knapsack. And that means respect back size, maximize profit.
So this is the shortest path.
No, not shortest. Here is we are just because of path. For shortest path also, I think we have a algorithm.
So the input graph is a general graph, no.
General
boundary.
No, nothing.
But instead of connectivity, like the last time you were looking at solutions that from a connected subgraph, now you want the path.
Correct, exactly. This is the second problem. Yeah, it's changing my problem. This is the second problem, path knapsack. Here, what is K? K is the smallest number of vertices in any solution. When I say solution, again, because this is not an approximation algorithm, I'm assuming I'm solving decision question. So I'm given target profit, size of bag, and so decision version. And so it can have multiple solutions. So look at the smallest solution. There the number of vertices. Suppose that is K. So this is a FPT algorithm parameterized by K.
So K is no okay.
Yeah, K is the smallest number of vertices in any solution. What are solutions? It respects backside and gives the target profit, which are input. I'm looking at the decision version here. Because I'm doing exact algorithm, no approximation. The idea is random coloring and dynamic programming.
This path knapsack looking at in connection to max flow.
Not I can think of. But I would suspect, max flow comes everywhere. If not max flow, you can have min cost, max flow. It's really at the boundary of polynomial time, and unless it comes, I won't be surprised if it comes here. It has a tendency to come in many places.
Flows.
Yeah, flows. Yeah, it flows. Okay, so to begin with, I can assume without loss of generality that K is known because I will run some algorithm which will work, which will give me the solution if I pick the correct K. So I will just start from K equal to 1, 2, and so on. Because given a solution, I can verify whether it's a correct solution or is it a junk. So for the rest of the algorithm, K is known. What I do first is I randomly color the vertices using K colors, just uniformly randomly. Pick a vertex, give any one of the K colors uniformly randomly, independent of everything else. And then I say a path is colorful if every vertex has different color. And for every subset of colors and for every vertex X, so this I'm done with the random color. Now I'm explaining dynamic coloring. Random coloring is just randomly color the vertex. So now what is the dynamic programming? This is the dynamic programming table which is indexed by every subset of colors and every vertex, this pair. And this is a Boolean table. This will be true if there exists a path ending at X which is S colorful. What do you mean by S colorful? Every vertex takes a color from S and every color appears exactly once. That is S colorful. So if there exists such a path, S colorful path ending at X, it is true, otherwise it is false. And here DSX, here I am doing the knapsack business. DSX here for every S colorful path ending at X, I am storing their size and profits. If there is none, then it will be an empty set. How I maintain this table? Here is this. Suppose I have a set of colors S and X. I know the color of X. This is chi of X, and I go over its neighbor. And ask, is there any S minus color of X colorful path ending at V? Because if there is a colorful path ending at a neighbor of V, which uses all colors of S except the color of X, I can extend that path to X using the colors of S. So if for any neighbor of X, I have such a path, then that path I can extend. So that is true. It is a big OR of these things. Otherwise, it is false. And if this is true, that means if I have a S colorful path ending at X, then we update Sx as follows. I look at every neighbor Y of X. If it has a sorry, it will begin S minus chi X comma Y. if there is a S minus color of X colorful path ending at Y, then this path S comma P, this tuple, for each such tuple, I add the size of X and profit S. Right, basically, so here we have minus S minus chi of X. So if there is a S minus chi of X colorful path ending at any neighbor of X, there I have all the stored tuples, and for those paths, if I extend to X, that means I just extend, add X to that subset. So the size becomes S minus S plus S of X, and price is P plus P of X. Of course, if there is no such path, then it is empty. Okay. So what is the running time of the algorithm? This PP table is indexed by all subset of colors and all vertices. So the number of cells is 2 to the power k times n, and this is polytime update. So it's big O of 2 to the power k times poly n. If I feed the correct k, and if indeed the random coloring makes the path k path colorful. Okay, so two things. One is path, if there exists a k path between X and Y, and if the random coloring makes it colorful, then my algorithm finds that path in this much time. What is the probability that if there exists a k path between X and Y, and the random coloring makes it colorful, is this. K to the power k is the total number of possible colorings, and k factorial is the number of colorful colorings, which is at least e to the power minus k. So if I repeat this random coloring business e to the power k many times, then if there exists a k path, I find it in this much time, 2e to the power k. And this algorithm can be de-randomized using the concepts of splitters with the extra factor of k to the power below.
What do you splitter?
Oh, there is some set family. It's basically, instead of trying random colorings, there are some set families, you enumerate them and of this much size, with the guarantee that if there exists a random coloring, then there exists a
Because so the whole concept of random coloring seems to be that you only want to you want to go from n to the k to something that is
correct,
only a function of
correct, e to the power, correct.
Oh, and because this is only required for small size sets.
Yes,
You
exactly.
can do with the smaller set.
It's only KY independence.
Yeah. KYC.
KY.
KYC. Okay, how much time do I have? Shall I stop?
10 minutes.
Oh, 10 minutes? Okay, sure. Oh, good. So let me again present something of different flavor. Till now, our base problems were polynomial solvable. Now our base problem is a hard problem, which is set cover. Let's recall. We are given a classical set cover in inputs. I have a universe collection of sets S1 to Sn. I need to pick a set cover. Each set has a size or cost S1 to Sn. That's the classical set cover. Now in the knapsack version, I have profits also P1 to Pm, and the goal remains as usual. You maximize profits subject to bag size, but your solution should be a set cover. For that, I will give a F-factor approximation algorithm. So what is F? I define frequency of an item to be the number of sets it belongs, and F is the maximum frequency of any item in the set cover. So this is the natural LP relaxation of this problem. This W should be S. So I minimize the sum of costs. So this algorithm is for minimizing the sum of cost given some target profit. So this is the minimizing the sum of cost. This is the set cover constraint, which says that for every element I in the universe, among all sets which contain that element, I pick at least one such set. And this is the profit constraint, that I am given a target profit D, and it to take this to Pi. Summation Pi xi is greater than or equal to D. ideally xi is 0 or 1 in ILP formulation. So xi equal to 1, meaning that you are picking that set, 0 means it does not, you don't pick the set. And the LP relaxation just set xi is greater than or equal to 0. Natural LP relaxation, but it has very bad integrality gap, simply because if you want fractional knapsack, and it will have the same LP. So this LP does not distinguish between fractional knapsack and an integral knapsack. So that's why it has a bad integrality gap. So what do? We write some other LP. So what is that LP? For every subset of sets A, such that the price P of A is less than or equal to target price P, I define the residual price PA to be P minus, this is the target price, minus the price that this set A is giving. That means after picking these sets, till how much more price I need to pick. This is P subscript A. Given A, the problem on the set F minus, suppose you have picked some sets A, then you are left with picking some sets from F minus A. KLF is the collection of sets from which you have to pick set cover, and here you have price target of only P of A. And because your price target is only P of A, for once you pick a set A, you can redefine the price of every set I to be minimum of its original price and residual price. So what is the LP then? You minimize the total size of the sets picked. Subject to, again, this is the standard set cover constraint. You pick at least one set among the sets where I belongs, and this is the price. For every set A, for every subset of A, exponentially many constraints. But this will be a primer dual kind of algorithm. So I will not be solving LP. I'll just be using this for analysis. So this is the primer, and I just write its dual as usual, and then very standard primer dual kind of thing. I build the solution iteratively. Let's call that A. A is the initial empty set, and I increase dual variables. So I have these dual variables Ya and Yj. I suppose increase Ys. I increase Ys until some constraint. If I keep increasing Ya, some of these constraint will become tight. Whichever constraint becomes tight, each constraint corresponds to a set. I pick that set. It's a standard primal dual algorithm. I pick that sets and I keep doing this until I satisfy my profit requirement. Once I satisfy my profit requirements, then I look at whether I have picked my set cover or not. Because then, if not, then I use these Yj's to satisfy my set cover requirement. That means if any element Ej is not covered by the sets picked till now, then I now increase these variables Yj. If I increase Yj, some of these inequalities will become tight. I pick the corresponding sets. Again, these inequalities correspond to sets, and I add those sets to my solution that I'm building and output that. This is quite standard if you are aware of primal dual algorithm. Yeah. So suppose X with a set of sets which are picked in the first loop, and we are running two loops, and small x is the indicator vector. So L gives sum of sizes of the sets in A. This is I divide into two parts: sets picked in the first iteration, first while loop, and set picks in the next while loop. Now I am bounding the first term here. Again, recall whenever I pick a set, this becomes tight, this becomes equality. So this equality is this, and whenever I have two double sum, it's always we try to extend the double sum. I extend the double sum, and then I So X is the set of sets between the first iteration, and what I show is that I bound these terms. So this term, I show that this is less than equal to twice P of A, residual price of A. And then this summation SIX is becomes less than equal to twice YA B. Okay. And then this becomes L, and the summation SI is this, and this is summation SIX. This is equal to FI again, because in the second iteration I'm picking sets whenever the inequalities become tight. If assuming is greater than or equal to 2, because if F is equal to 1, then all element belongs to only one set. You have no choice, you have to pick those sets. So there is an F factor approximation. I think here somewhere here I am using weak duality and so on. It's only weak duality is used and some form of approximate complementary is like this. Oh, but yeah, it's bit technical. Yeah, so that's it. I think. Yeah.
Any questions from the audience?
Are you creating Google image for a photo of yourself?
I downloaded this and now I try to mimic it.
What to say? That's a target.
Few days later, you got up. This is not AI generated.
Sorry?
I thought this is.
I forgot this. I picked from my old thing.
This
Last slide I
Google
do.
not here.
Yeah.
The problem is important. Is there something like general thing you can say about the graph, what problems become hard, difficult, and then basically just following the non-knapsack results also.
Yeah, so here, for example, we have two extremes. For example, let's look at set covers. You have set cover that restricts the valid solutions, but from knapsack point of view, you can ask two questions. You minimize cost and maximize profit, keeping one as input. This one minimizes the cost. But if you want to maximize the profit, I think you can show there is no algorithm, no architecture approximation algorithm. Basically, if you have an architecture approximation algorithm, you can use that to solve this, solve this set cover, correct? So at least for any no constant factor approximation algorithm. Yeah. So only these two extremes you can see. We have also studied hitting set, and either you have this same factor approximation, or you don't have any.
So any other question? So if not, let's kind of say again.
I stay away from activity, but only I want to say. Yesterday was a